Hello, good morning, everyone. We are going to start the session today. I'm Oscar Kamara. I'm professor here at UPF, and I'm delighted to introduce Professor Gunnar Cedersund from the University of Linköping in Sweden. Often we were discussing before when you see how researchers has been working in modeling in biomedicine for a lot of years. People were focusing in one organ, one particular type of physics, and work on this during a lot of years. And one of the main problems historically is that there weren't a lot of people trying to combine even multiphysics in a single organ or even in between different organs, which is really quite complicated. And it's impressive that Dr. Cedersund is one of the pioneers on trying to have a more holistic approach to modeling, because there is a lot of connection between different organs, and for some questions that the models need to answer, you really need to have these connections taken into account. Professor Cedersund studied theoretical physics and then did a PhD in Chalmers on modeling of biological system, and he has now a group of around 15 people.
Yeah, 15,
there.
20.
And again, it just impressive. I don't know how he managed to do so many different things, working in the heart, in the liver, in the neurovascular coupling with different people. But not only this, he doesn't stay on the, let's say, more basic science or research side. I mean, I've seen that he has projects where he's really trying to bring these models to a practical use, even to help on the patient communication, right? And this type of things that quite often we forget that these are very interesting applications and they can have an impact in the clinic. Not only this, I mean, you say, okay, I mean, you work on the modeling side. No, he also is quite involved in experimental models and trying to see how you can combine the information you get from the theoretical models with experimental data. And just another layer, I mean, he is involved also in the clinical translation and innovation. I mean, he is involved in a spin-off company, Sund is called, but also having a lot of projects with industry like AstraZeneca. So it's kind of the whole package. Looking forward to hear what you can explain about all these different aspects of modeling.
Very good. Thank you. Very nice presentation or introduction. One of the nicest I've gotten, I think. So, and also very to the point. It's exactly this type of putting things together, putting experimental data together with modeling, putting different organs together, and putting basic science to end usage together, that I will talk about. And to start off, I wanted to introduce a concept called M4-health. By the way, do you hear me fine? Good. So M4-health is short for Models for Health, but it's also an abbreviation for the type of models that we do. Let's see if I can point. Yeah, you see it a little bit. So the 4 M's are that the models are mechanistic, they are multi-level, multi-timescale, and multi-species. And I will, throughout the presentation, come to each of these words repeatedly. So basically what we have been doing is to spend the last 20-something years laying the puzzle of the human body, trying to fit together different pieces of knowledge, different data, this prior knowledge, time series images, continuous glucose monitoring, wearable sensors, into a digital twin, where it looks like you, both on the outside, and you will see some moving digital twins in the end, but also you can zoom in on the different organs and see what goes on in them when you do different things. And our goal and what we are working on is to connect these digital twins throughout your health journey. So from when you go to school You should be able to use your digital twin to learn about biomedical concepts, or maybe even physical or mathematical concepts. When you go to the gym, when you go to a concert, when you play a game online. And then when you start to need healthcare, maybe you start to wear some wearable sensor, maybe even during fitness you do that, and then at some point you need to go to the hospital, and then you bring your digital twin with you then as well, and to rehabilitation and even elder care. This is sort of the overall vision, that you have the same digital twin with you throughout your life, across different apps. So it's probably a very different app that you use for education compared to the one that you use in the ICU to decide what type of treatment you do for a stroke. But it's the same underlying digital twin in the background. So a digital twin that follows you across your health journey. And again, a digital twin is a computer copy of something. Can be basically anything. In industry, you often use it for an aeroplane or for a car or an engine or something like this. You have a digital twin for that. And here it will be in the literal sense of a twin that looks like you, so a twin of the human body of a specific patient. And here you see a digital twin of a tree. So here you see sort of a real tree, and here you see a decision tree, or a sort of symbolic digital twin. This is the logotype of my spin-off company that you already mentioned, which is called Sund, which is part of my last name. But that's not the only reason why we called it Sund. Sund is Swedish, and it means healthy, or to do things in a sound way. So the sort of subtitle to our company is called Sound Medical Decisions, where we want to inspire people, individuals themselves, but also doctors and other people that are involved with you to make sound medical decisions. And there is actually one more interpretation to this that I will come back to in the very end. But apart from having this spin-off company, I'm primarily a professor at Linköping University, and since very, very recently also at Örebro University, which both are in Sweden. And our research group also has a logotype, and it's this symbol here, which is a box where you can look inside. And that is because it's a mechanistic model. So we can see what leads to the prediction that we see. This is sort of beyond machine learning, maybe I should say. I consider what we do a form of AI, but it's not machine learning. And also, a thing that I will talk about a lot is that we always try to have all predictions associated with an uncertainty, so that you can distinguish between the well-determined parts of the model and the ones that have a high uncertainty. So, and maybe nowadays we should actually update this logo. We probably won't, because it doesn't look very nice. But we do hybrid models now as well, where we combine our mechanistic models, where you can look inside, with black box machine learning models. So this is basically my whole presentation in one slide. I will of course go through more details, but this is sort of the big picture. I think we have fairly well time, so if you have questions, you can either ask them at the end or just raise your hand or just speak out. We're not that many, so we can do this a bit informal. So, yesterday at dinner, I had lots of interesting conversations with different people, some of which we'll speak to tomorrow. And we came into this relationship between systems biology and mechanistic modeling and AI. So I wanted to add a little slide here, and I have a few more slides to sort of highlight the differences and the similarities and the way to interface these different types of models with each other. So here we have a mechanistic model that we will come back to a few times. It's very much in the details of things. This is how insulin binds to the insulin receptor, which then becomes phosphorylated. So it's really inside of a cell. And as you see, it's quite small scale. And this is a symbolic representation of a part of a bioinformatics network. And I will which is typically large scale. This is for the entire proteome or the entire phosphoproteome or the entire genome or something like this. And I will talk about how one can go from these type of models to these type of models by doing automated modeling. So where you basically automatize the process of doing these type of models all the way to this level. So that's sort of one way to bridge between them. Another is to combine the two models in that they do what they do themselves, and then you combine it in the end. So these type of models typically produce modules and biomarkers for which groups of genes is doing a certain thing. And the strength of these type of mechanistic models is that they can do simulations. And by identifying parameters from data, you can also get additional biomarkers. And I will show how both of these types of biomarkers or risk factors or other aspects will go into these hybrid digital twins that both have a bioinformatics part, a mechanistic part, and a machine learning part. And how this allows us to calculate the risk for a patient, but also to simulate how that risk will evolve depending on what the patient is doing with themselves. So this is another sort of one-slide summary of the whole presentation, and I will come back to all of these different parts throughout the presentation. And it's also sort of outline of the different strengths, so none of these can do the other's job, so to say. You can try to morph them into each other, but you can also have them do their own job and then combine it in the end, so to say. Okay, so I don't know how much you've seen historical breakthroughs in the previous days, but since I for once have plenty of time, which I'm very grateful for, I thought that I would take the time to do a little bit of a history of how modeling has evolved, so to say, starting from 1900, which was basically the start of modern physics. So you had physics, which is very close to mathematics, and then you have the things that are further away from mathematics. So you have biology, which is sort of still wants to understand how things work, and you have medicine, which basically wants to understand how to treat patients. And then in the beginning, you didn't really use any math in these fields, and as you know, you still only do it quite little. And the thing that you do the most, that most biologists and medical doctors use a lot, is statistics. Everybody uses t-tests all the time. And the first sort of attempt of combining all of these together came around in the 1950s, which was a guy called Norbert Wiener. He introduced the concept of cybernetics, which is a word that still lives on. If you go to the Eastern Europe and you go to a control engineering department, it's often called cybernetics. But also it's in words like a cyborg, for instance. So it sort of moved into science fiction. And the idea is to use mathematics to have a general theory for not only physics, but also biology and medicine and psychology even. And he didn't really succeed in that, but he did succeed in creating something called systems theory, which is basically control engineering theory. System identification sort of grew out of that. And this is what has led to the enormous explosion in engineering. This is what allowed us to go to the moon and do all of the technological revolutions that has happened since the 1950s. And at this time point, also these ideas of white box models, gray box models, and black box models was introduced, where these are the purely theory-driven models, where you basically don't use data because you already know all the constants which you do in physics. And these are the purely data-driven statistics or machine learning type of models, and where we try to sort of be here and branch out in both directions. And sort of out of statistics and applications to biology came bioinformatics. And for a long time, if you did systems biology, you didn't have a field of your own. So you went to bioinformatics conferences and tried to get a place in what they were doing. Or you went to theoretical biology conferences, which usually didn't use data that much. Maybe they had some general phenomenon that they saw that it was oscillations going up and down, and then they wanted to reproduce that. But it wasn't this sort of integrated way of using data to estimate parameters and so on, as they did in systems theory and control engineering. So it was when you started to combine all of these that systems biology in the year 2000 was coined simultaneously by different people. Hiroki Katana was one of them, who also started the International Conference of Systems Biology at this time point. And then for a while, bioinformatics sort of had a smaller place, which only deal with the statistics part. But now if you go to a systems biology conference, it's sort of very much bioinformatics there. And mechanistic models is sort of trying to find its place. And now with the invention of AI, or with the sort of extreme hype that we have of AI, there is really a fight for having a role of mechanistic models still. And this is where I think it's so important to understand this sort of distribution of labor between different types of models. And one of those things that allows us doing mechanistic models to sort of find a place is to talk about digital twins, which I already mentioned, and that I will talk about quite a lot. And this also is a basis for eHealth. So that was sort of some general introductions. Now I'll start to move into a little bit more details. But before I do that, I just want to, so I don't forget it, do some acknowledgements. So this is a picture of my group. It's a little bit outdated. We are maybe 10 more people now. Most of these people are engineering biologists doing mathematical modeling. But nowadays we also have some people doing experiments. We have a few medical doctors. We have some software developers and so on. And we work on a wide range of different applications, different medical applications, like diabetes and diseases in the liver, in the brain, immune deficiency type of things, and biomechanics. But we also now start to explore things like the arts, and I will come back to that. These are some of our key collaborators that typically provide us with data and knowledge. So we have used this sort of network over the last 20 years to develop mathematical models for the different organs in the human body. So these are references where I'm a co-author to scientific papers for all of the main organs in the human body, or at least most of them. And we've also worked a lot with combining these type of models, starting already in 2011 with the first publication, and then it's followed up since then quite a lot. And now also to personalize this into a digital twin, which we develop apps and interfaces for. So the general interconnected model become patient-specific by tuning it to patient-specific data. And we have some recent publications on that as well. So just to give you a feeling of sort of where we are heading before we dive really into the details and build ourselves up. These are some of the sort of general projects I'm involved with. So this is a collaboration with Auckland, where they have a very nice way to visualize the face and facial movements. And all the time here, when you interact with this digital twin, you can zoom in on the brain and see which areas in the brain is active. We work quite a lot with 4D flow data and blood pressure regulation on the short time scale, but also on the long time scale. We work increasingly with animations and with biomechanics. So here you see a digital twin of myself doing a little dance routine. And here you see the same twin, but without the skin and the clothes. So this is a simulation in what is it called? Not open pose, but open scene. Yeah, exactly. And here you simulate things like forces and so on. And the final level I want to mention here, just different things that we'll encounter during the presentation, is when you look inside the organs. So here you see a fat droplet disappearing from the liver. So you've taken out a little part of the liver, you put it in a microscope, and this is what you see. And then if you could see that when it's still inside the liver and you change your diet and you fast forward 2 weeks, this is approximately what you would see. You will see this type of fat droplets disappear if you change from a specific diet to a specific other diet. And underlying all of these different types of processes, the biomechanics and the metabolism and the blood flow and the brain activity and the things going on in the brain and the things going on inside the cells and the liver and so on, is mechanistic models. So I will now, with this little overview in place, look inside how these models have been developed and how we sort of iteratively check that they are correct, and if they are not correct, how we improve them. So typically a project looks something like this. So we have some different hypotheses. In this particular case, in a paper that was published in 2010, so some time ago now, we had 4 hypotheses for how insulin binds to the insulin receptor, this thing that I showed you a little while ago. And we had some initial data set that was sort of the basis for these hypotheses. So in this data set, we saw an overshoot, that when you added insulin, the phosphorylation of the receptor goes up, and then it goes down, even though insulin is still there. And the question is, why does it go down and not all the way down? So you sort of, that's what you saw. And that means that you need to have some kind of negative feedback. So these were 4 different types of negative feedbacks. And since you had that, they could all explain the original data set in 4 fundamentally different ways. And then we use the power of the mechanistic models. We can look inside the models. And we can do things like experimental design, where we do simulations with these 4 different hypotheses. And we do simulations with uncertainty, so we know which are the well-determined predictions and which are the not well-determined predictions. And then we look for an experiment design that gives a different prediction for at least one of them. In this particular case, it was the first hypothesis that had a different prediction than the other ones. And then we can tell our collaborator that if you do this one experiment, then out of the 4 hypotheses that you gave us, and that we at the moment cannot distinguish between, if you do this one experiment, we will be able to throw away at least one of them, because they can't all be right, because they have different predictions. And the predictions are with a low uncertainty, so no matter where you measure, you will not be in a sort of overlapping prediction with all of them. So at least one of them will be wrong. It turned out that it was the first hypothesis that was wrong. And then we went on like that. So, and here I want to point out that there are different reasons to do experiments. Sometimes you have so many uncertain predictions that you can't do this type of distinguishments. Then you need to find the most uncertain prediction and do an experiment where you measure that, because that will allow you to constrain the parameters the most, so that after that your predictions will be more well determined. So that's another type of experiment design, D2 here. And then you can go back to this unique and different. And then in the end, when you only have one, then you should always do at least one round of validation, where you test if the model can predict what will happen in the future experiments, and then only after that you do the experiment. So this thing that we did here is one project published in 2010. It took around 5 years to do, because it takes a lot of time to do each of these iterations here. And to sort of symbolize that, I sometimes use the term systems biology index 5 here. So all of this is sort of centered around the idea that in mechanistic models, rejections are important. So if you start out with plausible ideas of how you believe the system may work, and you can say it can't work like this, it can't work like this, it can't work, in fact, like any of the 4 original hypotheses, you need to have some improvement of them, a combination of them, in order to get a viable explanation. That sort of has evolved our understanding. And this is just an example of how this is done. So here we have this the last surviving of the 4 original hypotheses, which has a feedback, which is that the receptor leaves the membrane and goes into the cytosol. And it had a particular prediction that we see here with an uncertainty. And this uncertainty says that at least 45% of the receptors will have left the membrane and become internalized after around 20 minutes or 30 minutes. And here, for those of you who are into modeling, I want to go a little bit into the methodological detail and say that you can do this in different ways. So the most basic way that I would recommend is to use Monte Carlo sampling, which allows you to get the distribution like this for all predictions. But then once you have a prediction that you're particularly interested in, it's better to do a targeted uncertainty analysis using something called prediction profile likelihood, which is basically to do an optimization and see how small can the prediction be and how large can the prediction be while still agreeing with all of the data that you have. And if there are questions in the end, I can go into more methodological detail on that. And then you have this prediction with uncertainty. This particular model says that it has to lie up here in this area. And that means that it has a potential to be wrong. And in this particular case, it was wrong. So the experimental data was down here, 5%, which is way outside. Which means that you can't fit to this data and the old data at the same time. But we already knew that, so to say, because we had the prediction with uncertainty. Therefore, the hypothesis is rejected. And this is a key aspect of mechanistic model, to reject previously viable hypotheses. And a final note here on methods. I would really advise against using structural identifiability analysis and Fisher information matrix or sensitivity-based methods. And if you're interested in challenging me on that, which I hope some of you are, then I have lots of slides on that and lots of arguments for that. But I would really advise against using these and instead use these type of approaches. So just to make the basic ideas a little bit more clear, so here we have different simulations for different parameters that all are acceptable. They all describe the existing data. And then a well-determined prediction, which I sometimes call a core predictions. So remember the core inside the box. That would be here. And this here, one of these simulations is just a suggestion. And if you only have one simulation, it's just a suggestion, which is a very, very weak statement. And you could basically say that it says it could be like this, but it could be in some other way. And I have no basis to say that it should be like this. So that you could almost say lying on the beach, not doing any modeling anymore. So therefore, it's so important to have these uncertainties. And this is where you want to measure if you want to test a model or discriminate between models. And this is where you want to measure if you want to identify the parameters better. Okay, so let's see. So after all these 5 iterations, we ended up in this model here, which has not only the internalization, but also a feedback from downstream signaling. So all of these interactions are necessary. No simpler model can explain all of the data that we had. So this is how insulin binds to the insulin receptor, which we then went on to use the same approach to characterize how this then leads to increased glucose uptake, how this goes wrong in type 2 diabetes. And here you see data and models for both healthy controls and type 2 diabetes. So let's just take one of those to make it a little bit more clear. So here we see the data that I described before. Here you added insulin at time point 0, and then you measure the phosphorylation of the receptor. And you see that it goes up and then it goes down. And this is the overshoot. This was the original data set that everything started with. And then we went on to also connect with models for the other organs and describing their interplay. And then you get these type of simulations. So now we are in an intact body that we have given a meal. And the data here and in all other slides is the error bars. And the simulation is the line. This is the best simulation. And the uncertainty of the simulation. are these error bars here, or this shaded area, sorry. So the light blue area. So here you eat a meal at time point 0, and you look at what the specific organ is doing in terms of its uptake of glucose. And this particular model is already approved by the Food and Drug Administration for certain applications in type 1 diabetes. And basically what we have done is to add all of these details to that model. And also connected with long-term changes. So now we have the whole body, and we can simulate over months and years what happens, for instance, with weight and so on when you change your diet. And a key thing here that I will come back to in a little while is that we use arteriovenous difference data to do this subdivision into modules and to, in a reliable way, put the different modules for the different organs back together. But first, just to get everybody on the same page what type of models I'm talking about so far. It's where you have ordinary differential equations. So for those of you who do experiments, I hope you can follow it a little bit. And for everybody else, if you do other types of models, this is how you build up the types of models I've been talking about so far. Where you have this type of interaction graph. This might be insulin, this might be insulin receptor, and or this is the insulin receptor, this is insulin receptor that has been activated in some way. And this is some input that stimulates that activation. And this would be a binding reaction. So typically you develop these type of models first by identifying the states, then by specifying the reaction rates, then putting together the ODEs, deciding the measurement equation, and then putting together all of the parameters so that you know what needs to be estimated. So the states here, the things with differential equations, would be the sort of things that the arrows go between. These are typically things that might be concentrations of things. So this would be the concentration of the insulin receptor. So those are the states that you describe the dynamics for. And then you need to give these different reaction rates to this. Here you can use different approaches, either with the saturation, so some Michaelis-Menten type of equation, or mass action based, where you don't have a saturation. So all of these are different mechanistic assumptions. And if you put these together, this is what the ODEs look like. And then you need to specify what can you measure. In this particular case, you can measure the rate of the second reaction times an unknown constant, which is maybe what you can measure sometimes. And all of the parameters that you need to identify here are the ones appearing in the differential equation, which are the ones here, the initial condition, and the ones in the measurement equation. So all of these you need to determine from the data. Okay, so with this little sort of just getting everybody on the same page, if you're not familiar with these type of models, let's move on. And let's zoom in on one of the other organs. So this is now a much more recent paper, and where we have developed the liver in a better way. So the previous model, the one approved by the FDA, is already is here in the gray area. So here you basically only have plasma glucose and insulin and the crosstalk between those. So what we have been doing is to divide the glucose uptake into different organs. I talked about the adipose tissue before. This is where I had this insulin signaling and so on. Now I move into the liver, and a paper that was published last year. So here we have used all sorts of clinical data to describe how the liver's production of glucose goes down when you eat a meal, how liver glycogen goes up when you eat a meal. So the data are the different error bars, the simulation with uncertainty are the red areas. And again, estimation data to train the model, validation data to see that the model can describe new data. And this was published data here, so it could correctly describe this. But the key thing in this paper, and that we always try to do in all papers, is to have a prediction of something fundamentally new as well. Something that is available in no training data. So in this particular case, it is if you fast for 48 hours, you don't eat anything for 48 hours, and then you only drink protein after that. Then our model predicted you will see a rise in plasma glucose that you haven't seen any time before. If you do this before this sort of 48-hour fasting period, you won't see any change in the plasma glucose level because what you're drinking is only protein. So the model had seen no evidence that this would happen. But because of the mechanistic nature of what happens inside the liver, which has to do with how glycogen regulates these different fluxes, including the glucose production, which is the conversion of amino acids to glucose, which then in principle could be exported. Because it includes all of those mechanisms, it could predict that this is probably what will happen if you fast for 48 hours. So you have basically no glycogen left. Then if you drink only protein, you should see that in the plasma glucose. That was the prediction, qualitatively new prediction. And then the dots here are the experimental validation that we collected after the prediction was done. So this shows the power of mechanistic models, that you can predict something that is fundamentally new, that is qualitatively different from anything the model has seen, but you can still predict it because you describe the mechanisms, you describe what happens, and then you can go in new directions as long as the mechanisms are correct. So this is an example of that, and we try to have that in all of our papers. Okay, so these type of data, collecting data from different organs, is something that we are now doing in clinical studies, where we combine a large variety of different type of measurements. So let me see time. Yeah, good. Okay, so now we've seen how to build this type of small models. You test hypotheses carefully, and as I said, it took 5 years just to do this first little small model. It's a very time-consuming process. So how could you ever do this for larger models? Well, we have a suggestion for how to do this, which was just published in NPG Systems Biology a few weeks ago. And here we scale it to the phosphoproteome, where we have time series for 30,000 phosphorylations on 4,000 or 5,000 proteins. So this is the data that we have. And then we have this core model that I already explained. And then basically we automatize the process by replacing the manual searching of literature and reading papers with databases. So there are people that have structured this type of knowledge already into databases, where they have suggestions of which protein is talking to which protein. So we take such a suggestion and we use different types of rate expressions. I already mentioned mass action and mechanismental, but there are also others. And then when you tried those in different combinations, maybe you need several inputs, and you find one that works and that can predict at least some kind of validation data, so you save some of the data for validation, then you add it. And then you keep doing that, and all of these additions here are parallel problems. So you can put this on a supercomputer cluster, where each computer is doing its own protein. And then once you have done this one round, you have a much bigger model, so you can do a second round and a third round and so on. And as you go, you have to, if you want to describe all of the original 30,000 phosphorylations, you need to agree to use lower quality prior knowledge or lower quality interactions. So in the end here, it's basically purely data-driven. So then you are back to basically black box models, but with a flavor of a mechanistic nature. And this is reflected now in the accuracy of the model. So the inner layers here, they can with almost 100% accuracy describe at least which direction that the proteins will change when you do new perturbations that the model hasn't seen. But as you move throughout the layers and you come out to the purely data-driven layers, you are basically at something that is only marginally better than a coin toss. And here it's important to know that when you see these seemingly impressive p-values in bioinformatics models, maybe they have a p of 10 to the minus 10 or something like this. Then it is that it's so much more likely that it's better than random. So they are so much more certain that they are above 50%. And what we typically do in mechanistic models is that we want to describe all of the information in the data so that the only thing that remains is the noise. That's what our statistical tests do. So we basically see, are we as close to 100% that it's only noise that remains? Whereas bioinformatics models ask, typically, are we significantly above random? So it's two completely different levels of difficulty, which is important to remember when you compare the two types of models. And here you see that the inner layers have a much higher predictive ability. The outer layers, which are basically bioinformatics type of quality, they are marginally marginally but significantly above random. So now I talked about how we look inside the different organs and develop incrementally what happens inside the different organs. Let's talk a little bit about how we combine this together into the interconnected model. And the key thing here I already mentioned, that is to have modules, so each organ is a module, and to have input-output data for these modules. And this can be, for instance, this arteriovenous difference data, where you have an acceptable range of outputs for some inputs. So in the example that I already mentioned, we have glucose and insulin coming to, for instance, the adipose tissue, which you can measure using something called arteriovenous difference data. So you measure the arterial blood going into the tissue, you measure the glucose, you measure the insulin, and then you also measure the blood leaving the tissue. And the difference in glucose between the blood going out of the tissue and the blood going into the tissue is the glucose uptake. That's how much the organ has taken up. So in this way, you can measure what each organ is doing while still in the body. And this is super important because this allows us to translate all of the models that we develop based on in vitro data. So we know what happens inside the cells based on in vitro data, but we know what the cells are supposed to do inside the body. So it sort of allows us to link the in vitro and the in vivo data. And each submodel becomes an isolated modeling problem. So you can develop them independently of each other, and as long as they fulfill this input-output profile, they will talk together with all of the other modules and still provide good whole body simulations. So this is the way that we have used to avoid the error accumulation problem that happens if you only start to sort of characterize small models for each little part and then you put it together. Each of them is wrong a little bit, and then the errors will just accumulate and you have just a big mess in the top level. This is the way to bring stability to that you characterize what each module is supposed to do. And then the thing that the intracellular stuff is adding to that is what would happen, for instance, if you had a new drug here that you can only characterize in the beginning on the cells. But as I will come back to very soon, this is how you can go from those type of data to the whole body simulations. So, so far mostly signaling and metabolism. I want to say that there are other ways of doing this as well. So one thing that we work with quite a lot nowadays is to use carbon-13 labeled metabolites and something called elementary flux unit models. And this allows us to scale from the sort of handful of metabolites that I had on the previous model to tens or even hundreds of fluxes. So the key idea is to take out some part of the liver from surgery, and then you cultivate the cells in a medium that is labeled with carbon-13 tracers. You put the cells after a while, after they've eaten up these carbon-13 labeled metabolites, in a mass spec. So you see where they have ended up, how many are in each metabolite. And then you use the fact that you already know which metabolic reactions exist inside the cells to say that the only thing we don't know is how fast each reaction is flowing. We know which reactions there are. And we know where each carbon-13, or to what extent the carbon-13 labels ends up in the different metabolites. So then we can calculate, it becomes an optimization problem, to estimate how quickly must then each reaction have flowed in order to produce this distribution of carbon-13 labeled metabolites that you see inside the cells. So this allows us to measure the action or the rate of each intracellular model or reaction. It's a very powerful approach to do that, and it really is only possible if you combine these advanced experimental approaches with mechanistic modeling. There's no other way to do that. I know that some of you, at least, is doing also modeling of blood flow. So I wanted to just show one slide of how we work with this. So here you see an example of 4D flow MRI data. So here you have the beating heart, here you have the aorta going down to the rest of the body. And we use these zero-dimensional Windkessel models, which basically builds on the analogy of an electric circuit. So here we have different compartments in this system here, corresponding to the different colors, and each of them have a resistance and a compliance, which is basically how stiff the vessels are. And by fitting this model to these data, we can estimate all of these vessel properties throughout the system. So here we see the fitted model to this type of data. This is now one heartbeat, and the data are the different circles, and the simulations are the lines again. And then these estimated parameters become biomarkers that we can compare between different patient groups. So here we have without hypertension, here we have with hypertension, here we have without type 2 diabetes, with type 2 diabetes. So these are now different vessel properties in these different parts of the system that we estimate from this type of data, and we can see differences between different patient groups. So this is in one slide sort of what we do on the short time scale on these blood pressure regulations. I will come back to the longer time scale soon. So we also use these type of models to describe blood flow and blood flow regulation in the brain. So then it's basically how increased neuronal activity leads to blood flow changes in the brain. So here we see an example of what we can do with our mechanistic model. So here we stimulate the brain with a visual stimuli. Here we look at the vessel diameter in response to that for short, intermediate stimulation and long stimulations. So here we see a long stimulation, and the longer the stimulations are, we see that it becomes one peak and even two peaks. And because we combine a wide variety of different data from different systems, from humans, from primates, and from rodents. And in the rodents, you can use something called optogenetics, which allows you to stimulate only one cell type at a time. We can figure out what each cell type is doing, and figure out basically that the NO interneurons, so one cell type, is causing the first peak. The second peak is caused by the pyramidal, sometimes called excitatory cells. And the post-peak undershoot is caused by another type of interneurons. So here we see an example of the fact that we have a translational model that translates between the different species, where in the different species you can figure out different things. And what we translate is qualitative properties across the different species. So here we see new data. This is validation of cerebral blood volume and cerebral blood flow. So the model has not been trained to this data. And because we translate mechanisms from the preclinical, so the animal data, we can also for humans say that in these type of different responses, what are the different cell types up to? So we don't translate the parameters, but we translate the qualitative roles, so to say, of the different cell types. So it's a way to bring the information that we at least believe is preserved in the different species when you fit all of the data, but where you still allow for quantitative differences between the different species. So it's a sort of translational approach where you combine the knowledge that is available in the different types of data so that you can predict things that you normally could not predict based on the human data alone, because we have translated information that we had on the rodent data, for instance. So this is sort of the neurovascular coupling, how the blood flow is regulated in response to neural activity. And in the brain, we are now connecting this, so this is unpublished, with neural network types of data. So this is Hodgkin-Huxley type of models, which goes all the way to detailed ion channel models. And this is connected with this type of avatar type of data, where you actually can interact with the person that looks like a person, and that you can talk back to you. It will have an emotional response, and where different areas in the brain are active when you're doing that. And this in turn then is connected to the blood flow, which is and the biomechanics, which connects you to the rest of the body. So basically that's the different organs that are put together. So let's talk a little bit at the end here about applications before we open for questions. And again, you can ask questions anytime you want. So we have looked inside the different organs. Let's see how can we now use this model. So this is a collaboration that has been going on for quite a lot of years with AstraZeneca on drug development. And here we use again this multi-species approach. So we have a corresponding model for mice. So these are the same type of simulations that I showed you before with weight change here. This is a meal response, and this is the intracellular level. And simulations is the area, and data are the different error bars. And we also develop models for the thing that they are investing a lot of money in right now, which is to develop organs on a chip systems. So here we have a little liver, and here we have a little pancreas. And the pancreas is producing insulin, and the liver is taking up the insulin. Meaning that you get these type of data that you see here in the error bars, where you see a glucose consumption. So here we have more glucose, and then it goes down. And here they replace the medium, so they have, again, a lot of glucose, it goes down. And over time here, you see that the glucose consumption goes down. And that is because they managed to induce a sort of diabetes in this little system. But as you see here, in this little system, this sort of meal response, you could say, the eating of the glucose, takes around 2 days, 48 hours. And this is because of experimental limitations with the system. They cannot make the proportions between the blood flow and or between the blood, so to say, on this little chip and the organs, the same as in the human body. So there is too much blood compared to the organs. And there are also lots of missing organs that they don't have. But all of those are things that we can remedy in the computer. So in the computer, we can scale the volumes as we want. It's just a parameter. We can add the models for the other organs, because we already developed those. And then we can, in this way, do a translation so that we get from the 48-hour meal response that you see on the chip to the normal 2 to 4 hour meal response that you see in humans. So this is the translated response where you scale the organs and add the missing organs. And you can do the same, of course, if you add the drug here as well. So that you have a drug that you know what it's doing on the chip, and then we can use this translation to translate what do we believe this will lead to in humans. And this is the basis for a new type of knowledge-driven drug development. which is basically that instead of doing this type of linear trial and error-based approach, where you try lots and lots of candidates here on cell systems and then on a series of animal systems before you move on to humans, you let all of these different data from the organs on a chip, from the animals, from the cells, and from the clinical data go into this interconnected knowledge base, which is our multi-species, multi-level, multi-organ models. And that allows you to reuse also failed drugs. So failed drugs are no longer just wasted money. It's valuable information that goes back to the preclinical design of new drugs. And you can use this throughout the discovery phase for the translation to humans, which I already talked about, but also for the approvals and the sales part of drug development. So since I talked about this first, let me talk very shortly about the approval step, which is basically FDA's new guidelines for how to use mathematical models when you want to approve a new drug. And it's basically 5 criteria. The first is, can you solve the underlying mathematical model correctly? And for us, that's typically not an issue. If you do partial differential equations, it might be an issue. And then it's the validation part. So it needs to predict new data. And you need to have predictions with an uncertainty. And these are the things that I talked about a lot, that we always try to do. If you want to go all the way to validation, you also need to prove that the intended usage, the applicability, the application needs to be done in a way so that the validation evidence that you used up here is supporting the context of use. So it's almost easier to understand here. So here we have 2 parameters that sort of describe where are you using the model. You did the validation here. And if you are sort of using the model here as well, if this is where you want to prove that the drug or the medical device is useful, if this is where you're using the model, then you're fine. But as you are moving outside and further away to other types of usages, and maybe even where the original assumptions are violated, then the model becomes less and less of an argument in the approval process. That's basically these last 2 criteria. So just to illustrate this, so this is our patient 0. This is the first digital twin that we ever developed. And so we created this based on all sorts of MRI images and all sorts of other things, including this type of blood glucose data. So here we see the first meal that we used to estimate and personalize the digital twin for this patient 0. And then validation means that can you predict what will happen in the next meal, that here you eat something different. And then will we use the model for something similar, to basically to simulate not more different type of meal than that you used for the validation. If that is the case, so here you're not suddenly adding a drug that is doing something fundamentally different, but you're simulating the same type of variation that you did for the validation test. Then you basically fulfill the FDA criteria. Okay, second application, eHealth. So here we are basically using our digital twins together with a personalized data vault where the patient stores all of their wearable sensor data, healthcare record data, and personal diaries, together with a visualization device to communicate between all of the different front ends. The machine learning part is moved away to transfer learning to a variety of different databases all across Europe. And then we have different apps. Some are for deeper understanding, some are for meeting your goals at home. And in each of these applications, we have a series of steps that starts with interviews to identify the needs. Then we do sketches of the front ends. Then we do various workshops with the end users. And then we do prototypes all the way to minimal viable products. And then we start to test them clinically, which is sort of where we are now. And the idea then is again, to have different apps for these different steps, from prevention and home monitoring to acute treatment and acute monitoring, all the way to rehabilitation and revisits and reintegration of a normal life. And this is the basis for an EU project called Stratify, which has a budget of around 6 million euro, and that I happen to be coordinator of, and it's just started. So here we have clinical partners that you see in green here for all of these different steps that will help us with the integration. And we have technical partners that are experts on all of these different things here. So this is sort of the eHealth application. And again, a slide comparing eHealth in the traditional sense that most people use today, which is just to show data or communicate at a distance, where you don't really add an analysis of data, with what maybe is considered by many the most advanced thing, where you use AI, which can incorporate large clinical studies, omics data and images to get things like risks and features and classification, and also generated images. But the problem with AI or machine learning is that it doesn't add the mechanistic understanding, it doesn't use mechanistic understanding, and it's hard to generalize and hard to understand because it's a black box model. So what I'm advocating here is eHealth 3.0, which is to use this type of hybrid, multi-level, multi-scale digital twins instead, where you can do simulation of user-defined scenarios. You can gain and use mechanistic insights and still do risks. So these type of simulations that you can do here, and these type of bioinformatics simulations that you can do here, can go into the risk model so that you can simulate different scenarios. So here is a 40-year-old man coming to a health conversation. So this is in prevention. And then we can simulate different lifestyles and see what will happen to the risk of having a stroke. If he leads a healthy lifestyle, they will not develop diabetes or atrial fibrillation. But if he develops both, the risk is drastically much higher. In the same way for blood pressure. If you take a blood pressure medication, the absolute risk of a stroke will go down, so it's not until some 20 years later maybe that you will have the same risk. And the hypothesis here that we are working with in the clinical studies is that by seeing these type of different future scenarios for yourself, that will bring further impact to what the dietists and the nurses and physiotherapists and doctors and so on anyway are saying, and thereby increase motivation and compliance. So that's sort of the main thing that we are working on. But just since I'm anyway here, I just want to show that in this EU project, so this is the preceding EU project, we also, which is called Precise4Q, here we published a paper on stroke genetics. So this is a genetic risk score. It's published in Nature last year. And for decisions on the acute phase, some of the partners are already implementing decisions for that, where you add basically different details of what type of surgery you're going to do, and then you get the predicted probability that you will have a complication of the surgery, and basically advise should you do this surgery or not. So this is so far only machine learning models, but it's already to some extent implemented in the clinic. So this is part of this new EU project. And basically what we want to do now is to combine it all the way to the digital twins and the simulations of what happens. So in the scenario that I showed you before, where you had this 40-year-old man coming to a health conversation, this is one scenario where he will not change his diet. He will instead increase his diet to 400 more kilocalories per day, and then the weight will increase. And if you here at the end and in the beginning would compare plasma insulin, you will see that his diabetes, the insulin production is way too low, even though glucose is way too high. And on the intracellular level, this is probably what it will look like. In contrast, if he reduces the kilocalories per day by 100 and starts to exercise fairly moderately, then he will lose weight, won't have any major differences on the metabolic status, and the difference in risk between these two scenarios is big. And the again, the hope is that this will inspire people more than just saying it to them, by showing it to them on their digital twin. So one way to show it, and this is our first prototype, is to use this type of apps. So here we have a digital twin for a person called Gunnar. He's 44 years old, and this Gunnar has high blood pressure, so 145 over 110. And then here you see that there is a wide variety of different biomarkers that you can change or that you can look at. But let me just fast forward a little bit here. So now we added 2 different schedules, one with blood pressure medication and one without blood pressure medication. And then we click Add Simulation. This is sent to a server where the digital twins are stored. And then we see long-term simulations now of how blood pressure is evolving. This is systolic blood pressure, diastolic blood pressure, and this is the risk of a stroke again for the 2 scenarios. And this is where the treatment starts. So this is one way to show it. But I want to show another thing which might interest some of you, which is to make more realistic meta-humans. So MetaHuman is a software that's connected to Unreal Engine. And it's something that allows you to design by doing a 3D scan of the face of the patient. You get this type of scan, and then you can add all of the features that you want. You can add the clothes that you want and the skin type that you want. And then you can have these different types of avatars that you can change between. So this is from one of our current prototypes of an eHealth app. So here you change between different avatars. And then you can also, instead of just showing a curve of how the weight is changing, you can actually see the weight changing like this. And instead of just showing that you should exercise, you can say, let's see myself doing these different types of exercises. And instead of just saying this is what we believe would happen in the body, you can take away the skin and you can zoom into the different organs and you can see what happens inside the different organs. So, and also, instead of just showing in one environment, you can change between different environments. So you can design different environments depending on the application that you want to use. So, and this is what we'll do for the rehab phase, where we'll develop different home environments and also at the rehab clinic and so on. And then you can put all of this in a pixel stream that goes to the browser or to the application. Okay, so summary slide number 1. I talked about this digital twin and that it has a mechanistic part. And the mechanistic part allows us to incorporate data that AI cannot or machine learning cannot use, like mechanistic knowledge and regular papers, sensor data, time series data, data where you only measure in a few patients. And then at the sort of border here is multi-omics and images that can be used in both contexts. And the things that only can be used by machine learning models are the big clinical studies like UK Biobank and SCAPIS and so on. Sociodemographics and other risk factors that we don't know the mechanistic nature of, or if it's not time series. So these hybrid models that combine these with this, that allows us to simulate scenarios, to improve communication, and to use throughout the entire health journey. And from a patient perspective, you get a better understanding of your own health, and you get sort of personal advice from your own eHealth coach that follows you throughout life. And for those of you who do mathematical modeling, I said that uncertainty is very important, and the uncertainty comes to a large extent from the uncertainty of the data, which is propagated to the uncertainty. And this uncertainty is model specific. And if you don't do uncertainty analysis, you cannot draw any conclusions. Then you only have these beach statements. And if you have uncertainty, you can do experiment design, and you need well-determined predictions or core predictions if you want to test the model or you want to discriminate between different models. And if you want to identify the parameters, then you should measure uncertain predictions. You can use this for translation to humans and for integrating of different data. Then you need input-output of the different modules. you need to do things like isometric scaling of different parameters. And then you can replace different subsystem models where you have different degrees or different needs of details. So if you want to do uncertainty, my suggestion or my advice is to use profile likelihood if you really want the boundaries for a specific prediction or parameter. MCMC if you want to use it for all, but you need to know that it's not identifiable, the system. If you can't use any of those, use bootstrapping. And don't use Fisher information matrix or structural identifiability analysis. And the FDA criteria make sure that the usage of the well-determined model predictions are close to the applications where the validation has been done. And that's basically the method summary. So let's zoom out a little bit and think that you have now a digital twin and you go to a concert or you go to a conference like the VPH, then you can bring your digital twin with you. And you can see it dance up together with a professional ballet dancer that you see here. So here you see different digital twins. And when we have moved this all the way to augmented reality, then everybody will be able to see their own digital twin dancing on stage. Here you can't see it so well because it's just a mobile phone, so let me just show a little bit more. So it's me playing the piano, by the way. So here you have a digital twin of our dean at the medical faculty. This is of a major spin-off company of our university. This is a digital twin of myself. And here you can, all the time, if you want, look inside the organ, see what's happening. And in that way, sort of learn about your body when you do something completely different, like going to a conference or going to a concert. So, that was it.
Amazing, amazing. Any questions from the audience?
There was one in the end.
Yeah.
Hi, Terence McSweeney from the University of Oulu. Thanks for a fantastic talk. It's really interesting. I found the whole eHealth area and everything, really, really interesting.
Cool.
I hope I can kind of articulate this properly as a question, but you know, I see like there's a really strong pushback against personalized medicine in the sense of obviously there's been this great move from a paternalistic model of care that's like a top-down doctor or government or society tells you how to behave and how to be healthy. And that's all transitioned now to you collect data from your body, you then are responsible. And I suppose I have a sort of a fear with all this eHealth and the avatars and everything that these are these idealized versions of yourself, and this, like, patients are feel very guilty when they fail to do a rehab exercise. And if you're collecting all these complex biosignals, people are already overwhelmed, like a patient, for instance, and their heart rate variability. I mean, that's quite a hard concept to understand, and even scientists debate heart rate variability, and all of a sudden people are measuring that on a daily basis. Yeah. And so I suppose I'm just wondering what your opinions are as to, well, I can see you're very driven towards the making those digital twins that a person carries with themselves. But I'm just wondering where, like, at what point maybe should that be managed by somebody else or by the government or, you know, so do you get the direction of the question?
Yeah, no, it's an excellent question. And I think it's exactly those type of questions that we will move into now with this EU project, where we'll test this the 8 different clinics. So we need to get this type of feedback, basically, from the doctors, from the end users themselves, and also involve behavioral scientists and psychologists and so on, the people who know about these type of things, because it's super important, and it goes beyond what we as modelers normally think about. But if we want to make an impact, we need to address those things, because it can for sure backfire. And I think... Yeah, exactly. I mean, that will,
Iatrogenic consequence of
yeah,
that.
for sure. I mean, that will also be very patient-specific.
Yeah. Like MRI in lower back pain has a huge negative impact for a lot of patients, and it doesn't always like most patients don't benefit from getting an MRI for their lower back pain, even though it's such an amazing technology. And I have some of the same fears for all of this biosignal stuff in eHealth.
Yeah. At the same time as showing something personalized will make patients pay attention more. If they just hear general advice, which they do currently, they sort of zoom out a little bit. And but if they see an image, oh, that's actually me, then they respond in a different way. But maybe not always in a positive way. So I think that's one of the main things for us to investigate now.
Then Oscar will have to ask whether we have questions online too.
Great talk. Yeah, we had a nice chat yesterday during the dinner, but kind of a couple of technical questions.
Yeah.
In the models that you're building, you rely on MCMC. Okay, I have actually I have a couple of questions.
Okay,
in
go
fact,
ahead.
but let's start with MCMC. Basically, MCMC is good for perhaps fairly simplistic posteriors, unless you use different kinds of weird techniques. So, what are your posteriors really like when you do inference? Because the quality of approximation is subject to convergence of MCMC, and if the posterior of the model is really complex, then the uncertainty is not well modeled. So, like, how do you deal with those issues in practice?
Oh, okay, it stopped. Okay, So. I completely agree. MCMC is problematic if you don't have convergence, and you don't have convergence if you have two big problems with unidentifiability, and therefore you have problematic situations because typically you use the MCMC to figure out if you are identifiable or not, and then you sort of put the horse before the cart before the horse, so to say. So that's why I advise against only using MCMC. I see MCMC as a first step to get a feeling for which predictions seem to be well determined, which seems to not be well determined. And then once you have some specific predictions that you're interested in the uncertainty of, then you use a profile likelihood-based approach, which is not based on sampling the entire distribution, which, if you have unidentifiability, will contain infinite directions, which is the problem. You're never finished. But you're only interested in going in the direction in the parameter space that changes the prediction. And you want to go as far as you can in the parameters landscape that you can to get the maximum value. So you basically do an optimization algorithm that maximizes the predicted value.
So you get basically like hit a mode, basically.
Maybe that was what you would call it, yes.
Yeah. Okay, then it leads me to my kind of next question. Mm-hmm. During the inference in this type of models, you have shown already, kind of maybe in the beginning of your presentation, where you test different hypotheses. But that is subject to the causal graph that you build with your mechanistic model.
Yeah.
But humans tend to change their causal graph when they do experiments. Yeah. I'm not totally familiar with your field. I'm from machine learning background.
I know.
Where is your field heading? Do you are people in your field moving towards actually building experimental design, or basing experimental design over also the causal graphs, and kind of put humans in the loop, because you need to model the humans to know how likely with the next experiment that the humans would want to change the causal graph.
Yeah, I mean, I view what we do as a sort of formalization of what the experimentalists anyway do. So they look at the data, they try to learn some conclusions, and they think a little bit that, okay, maybe it could be like this, it could be like this, we don't know. So let's figure out an experiment that allows us to distinguish between those. Or it seems like this is the way it works, let's do an experiment that actually tests that. That's exactly what we do. It's just that we take the thoughts from their head and put it into a formalized objective so everybody can look at it form, and then we can put that into the computer and we can do the analysis properly. So we don't claim to do it in a way that sort of is independent of the human being coming up with the hypothesis. On the contrary, we are helping the human being anyway, planning the experiment to do it in a more powerful way, you could say.
Yeah, well, why I started to talk about this, because when I did my postdoc, I was in a group which was focusing on prior knowledge elicitation and kind of building AI-assisted prior knowledge elicitation. So how do you model humans to elicit the prior knowledge in the most efficient way? So that's, I guess, where I was heading.
I mean, the prior knowledge goes into the formulation of the graph, of the interaction graph. And often that is, so I mean, it's typically experts who've been in the field for 20 years. They will have their biases for sure, but that's unavoidable, I think. And most of the knowledge that they have comes from like reading thousands of papers and talking to many, many colleagues over many years. So it's not like you can say this is the source where it comes from. Let's do some objective analysis of the only source where they took their knowledge. Their knowledge is sort of almost by osmosis, being in a field for many, many years. And it is, of course, still based on bias and personal preferences and so on. But it's anyway a step in the right direction because it's objective. It's sort of made more objective. So other people can look at the model. They can't look inside their head, but they can at least look at the model. And then they can discuss the model, so to say.
Thank you. Questions online also.
Francesco Gualdi, University Pompeu Fabra. Very, very nice talk. It was really interesting. The world of personalized medicine, etc. I have a question about machine learning in this field. You represented machine learning as a black box, of course, during your presentation. Because of lacking of interpretability. And in recent years, we have witnessed this boom in machine learning, this increasing in the implementation of this technique. And I was wondering, especially, what is its role in personalized medicine in the future? So we are going to lose it or use it even more, or we need like more interpretable models? According to your view and your expertise?
Yeah, I think more interpretable AI or explainable AI, as they call it, I think that's a direction that they themselves move in quite rapidly at the moment. The things I have seen primarily that they do is to, for instance, highlight which part of the image is the machine learning algorithm using as a basis for its decision that you have a tumor or not, so to say, which allows the medical doctor to see that it's, okay, this seems to be where the tumor actually is. It's not based on the background or knowing or figuring out that it's on a specific machine. Or I mean, you can scrutinize the basis a little bit more based on that. You can't see the processes. But I think there is a clear division of labor. So I outlined one paper where we scale sort of from the mechanistic model to the omics level. But it's not really possible for us to scale all the way to sort of machine learning type of decisions, like the statistical things. And if you just have a big clinic, if you just have UK Biobank, for instance, where you have sort of one time point for 500,000 patients or individuals, and you know, did they get a stroke or not, for instance. That is a situation that is ideal for machine learning, and that we can't really use those type of data. So there you need to use that. But they can then not simulate what would happen if these different individuals would change their diet, or if they would start to exercise or take certain medications. For that, you need to understand the mechanisms. So there you need the mechanistic models. So I think it's really a division of labor. So there is a role for both, but they need to be combined and appreciated for what they can bring to the table. Yes. Yeah. Mm. Yeah. Yeah. No, I think it was on. Yeah. Yeah. Mm.
Or affects in any way the quality of the model or the predictions? Thank you.
Yeah. Yeah. Very good question. So the transfer learning that I mentioned is at the moment only for the machine learning models. So we have, in this EU project, we have 8 different hospitals. They each have their own databases with patients. And the idea, for those of you who don't know what transfer learning is or federated learning, is to have the data stay where it is. And then you move the model around. So you move the model around to learn the correlations and the sort of knowledge from each data. And then you in that way extract the knowledge from the data without actually moving the data. So you just move the model back again. I think that's sort of what you need to do because you can't, with current legal restrictions, move all the data into one place. The partner that is doing that is called TreeLogic. It's a company. They have done that in a number of previous EU projects. So they have the technology for it. Our own experience from the previous EU project called Precise4Q is that it's not that easy to transfer a model from one database to another. Even though you have the fact that the variables are not defined in the same way, but it's also different cohorts. And there are all sorts of differences that if you just take the model as it is and just move it, typically the performance is much worse. So you need to also adjust things when you move from one population to another population. And that's a whole field of its own, which I'm not an expert on. So there are some machine learning type of people that are focusing on that in the project.
We have 2 last questions around there. Yeah.
Yes. Hi, Joram Vodevoets, University of Pittsburgh. Actually, this is was going to be a follow-on to your question. So one way that it's I guess a comment and a question. One way you could merge mechanistic models with machine learning is through the use of the mechanistic model to generate synthetic data across a wider array of conditions than what you might have actual data on.
Yeah.
And when you do that, then you could potentially help to validate both types of approaches, right? Because you could generate a larger synthetic data set and then see how well whichever way you use the machine learning plays out when you do that. How robust is it, et cetera? Yeah. And likewise, you could use the machine learning part to again validate the larger scale behavior of the mechanistic model. So I don't know if you've thought about using this in this fashion.
I think, I mean, one reason to do that would also be to speed up the simulation. So if you have very costly simulations, you could actually replace the simulations with some simpler model that just maps from the parameters directly to the simulation, so to say. In our cases, we can get away still with co-simulation. So some of the models that we have in their most complex form are slow. But typically, we don't need to have all of those details. So we don't need to have all of those 30,000 phosphorylations, typically. So then we use a much simpler model for the... So basically what happens when a request is sent to our backend is that it looks at which variables you want to look at, and it looks at what you want to simulate. And then it puts together the appropriate submodels for each module, so for each organ. And it uses the simplest possible model for each organ. If that is not enough, so you have the need for a detailed simulation, so you need a very costly simulation, then we do a simulation for a number of different time points in the long-term simulation. And then we sort of interpolate, you could say, between those simulation output to get the, in a way, continuously changing simulation, also for the detailed simulations. That's basically co-simulation. So far, we have been able to get away with that. But I know that there are lots of people who explore to use machine learning models in the sort of the way that you outlined. We haven't done it, so I don't have any experience with it.
There was the last question here.
Thank you for the talk. I don't think I've ever seen all those tools put together in quite that way before, so I thought that was very interesting, and I'll probably go on to think more about it. I was just wondering, in some of your longer-term simulations, how do you handle aging? Because you would expect your parameter space to probably evolve over time, but you don't have patient-specific data for what somebody looks like 20 years from now.
Yeah, no, that's a very good question, and we have it to some extent. So we know. Typically, what we do is that we look at data from an organ, like the brain, for instance, where you combine or where you compare behaviors from different age categories. And then we do basically hypothesis testing, which parameters need to change in order to produce those changes that you see between the age groups. And in that way, we can introduce an age parameter into the mechanistic models. But then also, of course, it comes into the risk. It's the most important risk factor. So in the machine learning models, it comes in as a risk factor. But it also comes in to some extent in the mechanistic models as a parameter that is changing other parameters, so to say.
Okay, sure. Thank you.
Well, thanks again, Dr. Cedersund, for the interesting talk and the interesting questions from the audience. Let's have the coffee break then.